Good morning, everyone. It's really a pleasure for me to be here today at Kaggle Days Paris and to meet so many Kagglers and people passionate about machine learning and data science. And my name is Alberto Danese, and I will talk about one of the hottest topics nowadays in machine learning, that is machine learning interpretability. And in my opinion, this is really the key to a real adoption of machine learning for many industries. Let me spend just a few moments about myself. I'm a senior data scientist in Cerved. Cerved is the leading credit rating agency in Italy and a business information provider. And I work in the innovation team. Before joining Cerved, I spent many years in consultancy. I was a manager at Ernst & Young. Well, before that, I graduated as a computer engineer from Politecnico di Milano. Let me say that this could be the boring part, because the fun part is what I do at night time, because I'm an active Kaggler, obviously. I joined 3 years ago. Actually, I feel kind of ashamed because I only completed 8 competitions so far. That is really an incredibly low number of competitions, but let me say that I had a good conversion ratio, I can say, because I became Grandmaster after my 6th competition. And well, I won several medals. And last year I was lucky enough to win a prize in a Masters-only competition. So, I mean, I have fun, and winning a prize has been really a nice experience. So, let's get back to the topic. I will talk about interpretability, and I will cover mainly 3 areas. The first ones are the reasons for interpretability, why it is so important. And I mean, I think that some of them are quite obvious, but some others definitely are not. Then I will talk about how and when to use machine learning interpretability, and I will introduce a quick framework to, let's say, classify the different approaches. And finally, in the third section, I will deal with, I will make a drill down on a few techniques that I find to be very useful. So, why is machine learning interpretability that important? I cannot explain this concept well enough without looking at least very, very quickly at the history of artificial intelligence in just a slide. Because, artificial intelligence is not something really new. It was introduced in 1955, so it's more than 60 years old. And it has been through different phases, through different eras. We had the early days with the amazing work of people like Turing, Minsky, Rosenblatt, and many more. Then we've had a period of disillusionment. And after that, we have a period, if we just look at the last 20 or 25 years, we've had some amazing achievements from very different point of views. Because, I was a kid in 1996, but I can remember this milestone when IBM Deep Blue defeated Garry Kasparov, that at the time was the #1 chess grandmaster in the world. And so, I mean, this has been covered by the media extensively. But in the last 20 years, we have seen so many advancements from a technological point of view, with dedicated hardware, with graphic processing units, tensor processing units, and then so many free and open source languages, frameworks. I mean, both R and Python have been introduced in the early 90s. But another important thing is that also there has been an important cultural shift, let me say, because it was kind of amazing to see that all of a sudden dealing with data, with numbers, algorithms, has become something cool and something sexy. I mean, many of you probably read the article by Harvard Business Review that said that the data scientist was the sexiest job of the century. So, I mean, there have been a lot of things going on in the last few years. But the important thing is where we are now in 2019. And if we take a look, we have many important ingredients. We have 60 years of artificial intelligence. We have 20 years of machine learning accomplishments, results. And then we've had also an important cultural shift, cultural change, because data and algorithms have never been so valuable. And so I can say that artificial intelligence is basically everywhere, and machine learning solutions are widely deployed in production across all industries and across all companies. Or at least this is what you usually can read on websites, on newspapers, on magazines that talk about artificial intelligence. But if I have to be really sincere, when I read these kind of statements, my reaction is usually this one. Wrong, that's fake news, because, I mean, we still do not have machine learning everywhere. There are so many companies and so many industries that do not use machine learning nowadays. And I mean, I'm a Kaggle Grandmaster, hopefully a good data scientist, so I would like to prove my point with some data, let me say. Because I think that it's still early days for machine learning adoption. I read a few weeks ago this report by O'Reilly, where they interviewed more than 10,000 data specialists, so data scientists, machine learning engineers, data engineers, and well, they asked the level of maturity of the company they work for when it comes to model deployment in production. And it turned out that half of them answered that actually their company do not even have a single model deployed in production, not even one, a machine learning model, obviously. So there are still a lot of things to do. And in my opinion, we are really living in a two-speed world because we have technology-first companies like the tech giants that make a large use of machine learning. And I mean, they make a very frequent use of machine learning at scale on large customer bases, user bases, usually on not so crucial, not so important tasks for the user, like, I don't know, movie recommendations, targeted advertisements. So very frequent use, but on not so crucial topics. On the other end, we have banks, insurances, healthcare companies that really are still struggling to grasp the full potential of machine learning. And they make fewer decisions on ourselves, but they are much more important. For instance, a bank can decide to accept or to reject my mortgage, and this is something that has a real impact on my life. And you know, they are struggling mainly for two reasons, in my opinion, that are trust and communication. And basically, they both translate to interpretability, because, you know, these kind of companies, banks, insurances, or healthcare companies, usually work in regulated environments. And when you work in regulated environments, you have to be able to explain why you took a specific decision. And I mean, until a few years ago, it was impossible to use a neural network or a gradient boosted tree model and explain why the outcome, the prediction was that one. So they were basically forced to use some old school, let's say, statistical methods. But I don't want you to misunderstand my words, because interpretability is not only for regulation. There are many other smart use cases for interpretability. And I in particular like this example that is very famous in the field, that was introduced 3 years ago in the paper, Why Should I Trust You? And basically, the three authors of the paper trained a classifier to distinguish huskies and wolves, that are two similar animals, let me say. And they trained a bad classifier on purpose. At least it was not a bad classifier, it was a biased training set, let me say. Because every picture of a wolf had snow in the background, while every picture of a husky had no snow in the background. So basically the classifier was perfect, no mistakes at all. But then they applied it to a new test set, and they asked to 27 of their students if they were able to, on one hand, trust the model, and on the other, to highlight any potential features that could have an impact on this prediction. And they were 27, I mean, educated students, machine learning students, so not people taken randomly from the street. So this is, for instance, an image of an husky that was misclassified as a wolf. And after seeing this picture, 12 out of 27 students were able to tell that snow was probably important for this misclassification. So it's less than 50%. But after seeing the explanation that highlights the important pixels in the image, you can see a big patch of snow in the bottom right corner. And so 25 out of 27 students were able to realize that snow was really the important feature. So they were able to see that the classifier was not a husky versus wolf classifier, but it was a snow versus no snow classifier. So my point is that interpretability is very important also to understand if a training set is somehow biased, if it has any problems. Because in this case it was on purpose, but often you can have problems in your training set and the struggle to realize it. So I mean, I think that we have two great reasons for interpretability. One is related to regulation, and the other is related to a deep understanding of our machine learning models. So let me move to the second part, how and when to use machine learning interpretability. I would just like to introduce a few definitions that are kind of common in the field. First of all, what is interpretability? It's the ability to explain or to present in understandable terms to a human. This is kind of a general purpose, let's say, definition, but I like it. And then we have other three important points. The first one is the accuracy versus interpretability trade-off. Because on average, you can have accurate models with approximate explanations or the other way around. But you have to find, let's say, a good balance between the two. Third definition actually, is global versus local interpretability. And this is very, very important also for the following slides, because when I speak of global interpretability, I refer to the fact that I want to explain how a prediction acts on a whole data set. While when I speak of local interpretability, I refer to the ability to explain a single record, for instance, a single row. So being able to say why that row has been given a specific prediction. So this is the local one. And the last definition is model agnostic versus model specific interpretability. When I speak of model specific interpretability, I refer to models that can be applied only to neural networks or only to gradient boosted trees or so on, while model agnostic approaches can be applied basically on every prediction. And then I would like to introduce the different levels of interpretability, because you can act really in not only in one place. The first one is the data level, and I will not talk about it extensively because it is not a technological issue or not even an analytical or methodological one, but I would just like to underline that you have to understand the processes that your data undergoes, because your model is only as interpretable as your data, so you have to really understand the domain, in my opinion. The second point is what you can do before building a machine learning models. Because there are some, let's say, expedients or some tricks that I will show you in a while that can be applied when you train a model, so when the model has not yet been built. And in this way, you can enforce some specific properties, for instance, in your model. And then you can explain the model after it has been built on a global scale or on a local scale, as I told you earlier, so on a whole data set or on a single record. So this is the quick framework that I'm going to use. I will tell you the name of the approach, for instance, and explain the main concepts. Then I will define if it is something that you have to do before building a model or after building a model, and if it applies on a local or global scale. Then I will tell you about some restrictions. I like the fact that I would like you to be able to understand what you can say to your manager, for instance, or to someone in charge when you apply that specific interpretability model. And I will focus mainly on structured data, so on tabular data. I think that the following speaker will focus on images and text. So let me make a drill down on a few of these approaches. The first one that I really think it's kind of underused is monotonicity constraints. And here the idea is really pretty simple. First of all, it's something that you have to do before building a model and that acts on a global scale. So you see the B and G in the top right corner. But monotonicity constraint is based on the fact that in many real-world problems, we expect some features to be monotonically related to the targets that we are trying to predict. And let me make a simple example. Let me say that we want to evaluate an apartment. So we are in the real estate world. And we have the floor surface. We expect the floor surface to be monotonic with respect to the final price of the apartment, because if I have two apartments that are in the same place, at the same floor, with the same quality, we expect the larger one to cost at least as much as the smaller one. So this is exactly a monotonic relationship. And the bad thing is that when we use, let's say, a greedy algorithm like LightGBM or XGBoost, it usually catches up some small irregularities, some small mistakes, and basically it cannot you cannot have the guarantee that the final prediction is monotonic with respect to that variable. It can be really a problem when you have a prediction that behaves in a strange way and you have to explain it. And the point is that there is a feature that is, I think, underused in both LightGBM and XGBoost that lets you specify monotonic constraints. And in this way, when you apply this feature, and I will show you in the next slide, you can say that when all other features are equal, your feature X, increasing your feature X, for instance, will result in a monotonic behavior of your target, of your predicted target Y. And let me show you an example. This is a simple parabola. It is y equal x squared plus some added noise, some added Gaussian noise. And it is, let's say, a one feature, one target problem. So I just try to fit a light GBM in a let's say, classical fashion. So with a train set, test set, and so on. And you can see that light GBM manages to fit the curve, but even if the trend is monotonic, locally it can show a negative derivative. So you have a behavior that is not expected, like in the patch that I highlighted. But there is a simple parameter that is monotone constraint that lets you set a non-descending or non-ascending monotonic constraint on the variable. And this is the fit that you have when you set monotonic constraint. You can see that the derivative is always non-negative, and so it is a much better fit. You have to be careful, obviously, because if you, by mistake, you set the monotone constraints the other way around, so you set -1, like a descending constraint, the light GBM cannot find even a single valid split, because, obviously it cannot find one. And let me show you that, monotonic constraints can be also useful from a performance point of view, because they have kind of a regularizing effect. And in this example, you have that the root mean square error of the constrained model is better than the root mean square error of the unconstrained model. So the blue one is better than the red one. So you have two results with a single parameter, let me say. You have a model that is more explainable because it behaves regularly, let me say. And then you also have a better performance. And so this is an example of what you can do before building a model. Another example, I will just leave you the title, is optimizing a custom metric. This is another thing that you can do before building a model. And when you optimize a custom metric, there are different ways to do it. You can say that your model directly maximizes or minimizes something that is not maybe the usual root mean square error or area under the ROC curve or so on. And this is another thing that you have to do before building a model. Let me switch to another case, what you can do after you have built a model on a global scale. So let's say you have built a model. Usually you plot the important features, like with XGBoost, with LightGBM. It's kind of straightforward, but you do not know why these features are important and how they impact the prediction. This is what you can do with partial dependence plots. I will show you an example again with R and the PDP package. And the idea is that the partial dependence plots average out the effect of all the other variables and just show you how a single variable that maybe is the top one, top two, one of the most important ones, how this variable behaves with respect to the predicted target. So it is usually made 1 against 1, so one feature, one important feature against a predicted target, but it can also be done with 2 features and the target, the predicted target. And so you can see the average behavior of a specific feature with respect to the target. Let me show you an example. This is a partial dependence plot. The first 2 images are taken from a real estate data set, and you can see how the overall quality of the area have an impact on the average prediction of an apartment. And on the right, you can see another image that is a 2-feature PDP, a 2-feature partial dependence plot. And in this case, we are using colors to show the target, the predicted target. And the 2 variables are on the X and Y axis. So it is very, very, very important to use partial dependence plots because, feature importance is not enough when you use like a gradient boosted tree. And let me move to the third area that I wanted to cover, that is what you can do after you have built a model on a local scale. There are a couple of interesting approaches. I will describe especially the first one, that is LIME. LIME is local interpretable model agnostic explanations. And it was introduced 3 years ago by 3 researchers. By the way, one of these researchers is a co-author of XGBoost, so the world of machine learning is not that huge, let me say. And the idea here is pretty simple. It assumes that locally, even complex models can be approximated with simpler models like linear ones or simple tree-based models, not gradient-boosted trees, for instance. And so it works in this way. I will show you an example. First of all, you have to take a record that you want to explain. So you have a record with all the features and the prediction. Then you do the perturbation phase. So you basically create artificial samples from your original data set, and you get the black box predictions of these artificial samples. These artificial samples are taken everywhere in the space of the features, let me say. But then in the second phase, they are weighted with respect to their distance with the record that you want to explain. So this kind of weighting is based on a proximity concept, obviously, and it is used in the third phase to fit a linear model, or anyway a simple model, in a weighted fashion, let me say. So in this way, you have a model that locally is explainable because it is inherently explainable, and you can find the explanation as the simple coefficients of the linear regressions, for instance. This approach works on tabular data, but it works also on images and on text data with some tricks, let me say. And also the example of the husky versus the wolf is taken from this paper. And I mean, with LIME, you can say that a specific prediction is impacted by some features with a specific, let's say, contribution or relevance of each feature. That can be positive or negative, obviously. And this is a quick example built with the R package LIME. The idea here is that I'm trying to explain 3 predictions of house prices. And I chose to highlight the most important 8 features with LIME. And what I want to show you is that the most important feature for the first case is not the most important feature for the second case. So I mean, every case is impacted differently by different features. And they can have also a different impact. You can see the positive or negative impact of each of the features. And this is one of the approaches of local interpretability, let me say. The other one, very, very famous one, I would say, is Shapley additive explanations. I would just tell you a few words about it. It has a completely different approach with respect to LIME because it doesn't make assumptions of local linearity, let me say, but it uses game theory to explain predictions. So the prediction is basically seen as the outcome of a game theory problem, game theory coalition problem, and the features are the player that fight to win the outcome, let me say. It is not easy to explain it in 2 minutes, in my opinion. But the idea is that you can have a prediction, you can have an explanation, let me say, also locally. And so for each feature, you can have the exact contribution of each feature. And the good thing is that there is a fast implementation on gradient boosted trees that is available, at least as a Python package. And I tried it, and it is, I mean, really good. So different approach from LIME, because LIME makes an assumption on local linearity, while Shapley does not. But they are both useful approaches, let me say. So let me show you this table that I think it's important to pinpoint the important topics. I think there are three kind of needs that you want to achieve, let me say, when you use machine learning interpretability. The first one is enforcing some kind of behavior, of expected behavior in your machine learning models. You don't want to leave it completely free, let me say. And it's the example of real estate and of the final price of the apartment with respect to the floor surface. And in this situation, you have to act before building a model, obviously. And for instance, you can enforce a monotonic constraint. The second kind of need is when you want to show on a large population, on a large data set, let me say, how a single feature impacts the prediction. For instance, I make you an example from the healthcare world. You want to see how the numbers of cigarettes impact the likelihood of developing some kind of illness, for instance. And in this case, you have to use typically feature importance first to understand the important features. And then on these important features, you can do a PDP, a partial dependence plot, and see how they behave, let me say. And third need is understanding a single prediction. So we're talking about local interpretability. And I would just like to make this example that, in my opinion, is kind of interesting because, you know, customer churn is one of the usual use cases of machine learning. And you typically end up with a probability, let me say, that for a customer to leave your company within, I don't know, 3 months, 12 months, whatever. The good thing is that if you apply Lime and Shapley, you are able to add the important reasons why that specific customer is likely to churn. So you can have two customers that have the same probability of churning, but for very different reasons. And with Lime and Shapley, you can see what are the reasons. And then, for instance, you can talk to your marketing department or to whoever in order to have a proper campaign to address the different, the different reasons why they are leaving. So it's very important, in my opinion, to use Lime and Shapley. So I think let's wrap up. It was quite overrun, and I gave you, I think, a lot of information. But I want to remember this important stuff. First of all, there are many reasons to study interpretability, and I would say that the most important ones are, on one hand, regulation, because in regulated environment you have to respect the regulation, obviously, and the other one is having a fair, robust, transparent machine learning models. And those understanding maybe if the training set has some problems, so let's say have a deep understanding of your machine learning models. Then I would like you to remember that there are many ways to do machine learning interpretability. There is not only Lime, only Shapley, for instance. You have to think about 4 different levels. So data first, then what you can do before building a model, like enforcing constraints in some cases, and then you have global or local explanations that are the other two levels of interpretability. This is a pretty new field because, you know, the paper of Lime, for instance, has been introduced just 3 years ago. And so nowadays, high-performance models like gradient boosted trees have a reasonable degree of explainability, of interpretability, and it's important to know. And I think that basically an interpretable model is usually more robust, more insightful, more actionable than a classic black box model. So it's a better model. And so I'm leaving you just a few links in case you're interested in understanding something else. They are very, very interesting links, and thank you very much for your attention. I think it's Q&A time. By the way, I will be around 5 minutes. 5 minutes of Q&A. I will be around in these 2 days anyway. Anthony.
Do you know if empirically Shapley and Lime typically give you similar results?
Typically they do not, but there is an important point that Lime makes a strong assumption on local linearity, and there are, a problem with Lime, I show you just quickly, is that, here it is, when I say perturbations and weighting, it's easy to understand what it means to make a perturbation or a weighting, but how do you weight the distance of your artificial samples with respect to the one that you want to explain? This is the tricky part. So they do not give Lime and Shapley the same result. On one end, actually, Shapley is usually considered more reliable because it has a strong theory behind it, that is game theory, coalition game theory. But again, it has to be interpreted because, for a single record, you have the different contributions of the various features. But it doesn't mean that if you change one feature, you can just subtract the contribution of that feature. I don't know if I make myself clear, but they have both. They are not the same approach, and they give you different results.
Hi, I'm Diogo from Lisbon. Very interesting presentation. I had two questions for you. When you talked about optimizing for a custom metric, I was just curious. When you compete on Kaggle, don't you always optimize for the given evaluation metric? That was just one question. Second question is, on Lime, you do perturbations. Actually, this is the slide. I was going to ask you, how do you do those perturbations and measure the distance for categorical variables?
Okay. I'll answer the first question first. So custom, you are referring to the custom, this one, custom metric. This is what you do in many Kaggle competition where the evaluation metric is not a standard one. So it's not root mean square error and AUC. So I mean, I don't know if I understand your question properly, but what you do when, for instance, on XGBoost or LightGBM, when you define a custom objective function or a custom evaluation function, what I told you here is exactly what you do on Kaggle, because you do optimize that kind of metric. Here I'm trying to say that also in the professional world, let me say, sometimes you do not have a standard metric, and it is a good thing to do to optimize a custom metric, so you can say that your model directly optimizes that target. And the other question was on Lime. On the categorical variables on Lime, well, first of all, what you typically do not have to do is doing one-hot encoding, because when you do one-hot encoding, let me say that you have four different a feature with four different levels. If you do one-hot encoding, you typically lose the relations between the first and the four variables. And during the perturbation phase, you cannot enforce the sum of this one-hot encoding to be 1. I don't know if I made myself clear, but you know, it's important, let me say, not to make one-hot encoding. You can encode like use frequency encoding, for instance. So you basically give a different weight to the most frequent class. Okay, any more questions? One over there. Or okay.
Could you raise your hand again?
Okay. Hi, Alberto. Thank you so much for your talk. Before, you show us that we can use a monotonic constraint. And it is possible to deactivate it or to say they are increasing or decreasing, no? But are we able to say to LightGBM which variables has this constraint?
Yes. Because I showed you just a quick example, one feature, one target. If you have, let's say, 100 features and one target, you just have to give LightGBM or XGBoost a vector of +1, zeros, and -1. So if you want to constrain the first variable to be ascending, you set +1. The 100 variable to be descending, -1, and the other one, you just leave them at 0, and they are unconstrained ones.
And does LightGBM discover this kind of constraint by itself?
And then basically it rejects any split in the trees that behave in the other way with respect to the monotonic constraint. So it never splits against the monotonic constraint. That's the way how it implements. It's a little bit more complicated, actually, but.
Thank you.
Thank you. So just thank you very much.